In this video, I'm going to walk through the solutions to two example problems related to electronegativity and overall polarity of a molecule. So let's start with this one. Hopefully you've had a chance to try both of these. We're going to rank these atoms in terms of least to greatest electronegativity. You can use this by looking at the overall periodic trend, where it's my periodic table, my very brief one, where it increases, we go up and over on the periodic table. If I do that, I can look at this and see that my oxygen would be the closest to my fluorine, so it would have the highest electronegativity. And then from there, my sulfur is closest, and then bromine, and then hydrogen's furthest away, so it would be the lowest. And so that's just looking at where these are placed relative to each other in the periodic table, thinking about fluorine as kind of my highest point for electronegativity. Now, if I look at my electronegativity chart and look up these values, bromine is 2.8, sulfur is 2.5, hydrogen is 2.1, and oxygen is 3.5. So looking at this, I see that there's a bit of an upset in how I approached this with my sulfur and bromine, just going off the periodic trend. So these would rank from highest to lowest of oxygen, followed by bromine, then sulfur, and then hydrogen. You'll have this electronegativity chart on exams and quizzes, so we'll default to this as correct, but I hope that this exemplifies that there's a bit of a gray area here. I'm thinking about the electronegativity of sulfur and bromine. Let's try looking at these molecules that we already determined the geometry for and think about whether or not they're polar or nonpolar. And we'll add one more in here, HCN. So looking at carbon, and I'm going to tetrabromide. I'm going to draw this in 3 dimensions to kind of help us out, using my wedge to say that I have a bromine coming out of the plane of the screen and a dash to say it's going back. In this case, my bromine is a 2.8 and my carbon is 2.5. So if I look at the electronegativity difference of this, it's 0.3, and that is less than 0.5. So I actually don't have any polar bonds here. And so I won't draw anything. I won't put any arrows or partial negative and partial positive signs. I'm just going to write nonpolar. All right, next up is my phosphorus and hydrogen. So phosphorus had that lone pair that created a trigonal pyramidal geometry like this. And so I'll compare my phosphorus, which is equal to 2.1 for my chart, and my hydrogen, which is 2.1. I have an electronegativity difference of 0. So again, this is a nonpolar molecule. All right, my CH2O we've seen already, but here we go. So this is 120 degrees apart on each side, and we only have one polar bond here. My carbon is 2.5 and my hydrogen is 2.1. So that's a 0.4 difference between the two. So that's nonpolar. My carbon or my oxygen of 3.5 and my carbon of 2.5 has a difference of 1.0. So that is polar. So I have a polar bond between carbon and oxygen, which I'll indicate with a dipole moment arrow like this, or with a partial positive symbol on carbon and a partial negative symbol on oxygen. Now, since my carbon-hydrogen bonds are nonpolar, there's nothing to cancel this out. And so this will have an overall polar, will be an overall polar molecule. Now let's look at hydrogen cyanide, which was our linear molecule. So we've just determined here that our carbon and hydrogen bond is nonpolar. Let's look at carbon and nitrogen. So carbon is 2.5, nitrogen is 3.0. We have a difference of 0.5. That is just barely enough to be polar. So carbon's less polar than nitrogen, or less electronegative. So I'll put that plus symbol of my dipole arrow by the carbon and the arrow pointing to nitrogen. You could also put a plus symbol on carbon and a delta negative symbol on nitrogen. And so there's nothing to cancel out this arrow, nothing pointing in the opposite direction. So this will be overall polar.